So
Okay.
wait a second, sir. Yes, sir. Now,
So good evening, everyone. First, I should apologize for starting 10 minutes late. I'm not very good with the technology. My name is Tejinder Singh. I am a physicist at the Tata Institute of Fundamental Research in Mumbai, and I work on quantum gravity and the unification of forces. Can you hear me clearly?
yes, sir.
So, the title of the talk is Elementary Particles and the Magic of the Octonions. There will be three parts to this talk. First, I'll tell you what are elementary particles. Then, I will tell you what are octonions. And then, I will tell you what octonions have to do with elementary particles. Elementary particles. Everything, as you know, in our universe is made up of atoms. From things around us on the earth, living things as well as non living things, and everything in the universe, like you see the galaxies that you see in this picture, everything, as you know, is made up of different kinds of atoms. What is inside the atom? There are three different kinds of particles: proton, one or more protons, which have an electric charge which is positive, which we will denote by the symbol plus E. Then there are neutrons, which have electric charge 0. The protons and neutrons, as you know, together form the nucleus of the atom. And in orbit around the nucleus are electrons, which have an electric charge minus E. So the charge of the electron is equal and opposite to that of the proton. The electron is an elementary particle, meaning that as of today we think that it is not made of anything else inside it. It is what it is. However, protons and neutrons are not elementary particles. They are made of something else known as quarks. The protons and neutrons, as I said, are made up of what is known as quarks. Two different kinds of quarks make up protons and neutrons. The down quark has an electric charge of minus E by 3, that is, one third the charge of the electron. The up quark has an electric charge of plus 2E by 3, that is, two-thirds the charge of the proton. A proton is made up of two up quarks and one down quark. You add two up quarks, it is 4e by 3. Add a down quark minus e by 3, 4e by 3 minus e by 3, 3 by e by 3, which is e. Good. A neutron, on the other hand, is made up of one up quark and two down quarks. So let us add. Up quark is 2e by 3 and 2 down quarks is minus 2e by 3. The sum is 0. That is why the neutron is neutral. So everything inside the atom, we know, is made up of down quarks, charge minus e by 3, up quark, charge 2e by 3, electron, charge minus e, and another particle known as the neutrino, which has electric charge 0. A neutrino does not sit inside the atomic nucleus or anywhere in the atom, but it takes part in conversion of neutron into proton. And a neutron will decay into a proton if it is not inside the atom, giving also a rise to a electron and an antineutrino. I'll soon explain what is an antineutrino. So please remember, there are four different kinds of elementary particles listed here. Pay attention to their electric charge. 0, minus E, 2 by E, 2 E by 3, and minus E by 3. So you can already see that there is a pattern. Okay. All particles have corresponding antiparticles as well. An antiparticle has the same mass as the corresponding particle but opposite electric charge. The things inside the atom are what we call matter, and antiparticles constitute what we call antimatter. Almost entirely the universe today is made up of matter. There are very slight traces of antimatter, and we do not know the answer to this question: why does matter dominate over antimatter? It is a deep unsolved problem. So let us look at what are antiparticles. Neutrino has zero charge, the antineutrino also has zero charge. It would appear as if the antineutrino is the same as the neutrino. The neutrino is its own antiparticle, but that is not clear even today. It is a subtle unsolved problem. The down quark we saw in the atom has a charge minus E by 3. The anti-down quark has a charge plus E by 3. Up quark is 2E by 3, and the anti-up quark is minus 2E by 3. The electron is minus E, and its antiparticle, known as the positron, is plus E. So, what do we conclude from here? The universe has more matter than antimatter. The antiparticle has the same mass as the particle. And notice this very interesting point. Only these values of charge are observed in nature. If you look at the ratios of the electric charges in their absolute value, it is 0, 1/3, 2/3, and 1. 0 for the neutrino, 1/3 for the down quark, 2/3 for the up quark, and 1 for the positron, and minus 1 for the electron. So there are only 4 values of electric charge ratios allowed in nature. Why should this be so? Until recently, the answer to this question was not known. And one of the things that I will tell you in this talk is that the numbers known as the octonions give us a beautiful explanation and answer as to why only 4 possible values of electric charge are there. The octonions we'll use the octonions to prove this result. Then there are something called 3 generations of particles. So as if there is child, say son or daughter, parent, let's say daughter, mother, grandmother. That's why we call it generations. 3 generations. Every particle that I listed so far, I listed 4: down quark, up quark, electron, neutrino, and their antiparticles. Every one of them comes in 3 generations. Then they all have the same electric charge, only their mass changes. Electron, second generation muon, third generation tau lepton, all have charge minus E for the electron family and plus E for their antiparticles. It will be positron, anti-muon, anti-tau lepton. 3 generations for the electron family. Similarly, 3 generations for the down quark family. Their physicists give something, not very systematic names, anything that comes to their mind. Down quark, strange quark, bottom quark have mass electric charge. All of them have minus E by 3. But here, by the way, the muon is heavier than the electron. The tau lepton is heavier than the muon. Similarly, down, strange is heavier than down, bottom is heavier than quark. How much heavier? I tell you in a moment. Up quark, charm quark, top quark are the 3 fermion generations. All of them have electric charge 2e by 3, and all of them will have antiparticles, and they differ only in their masses. Similarly, the neutrino. There are three neutrinos: the electron neutrino, the muon neutrino, the tau neutrino, all have different charges. And what changes as you go from one to the other in a generation is the mass. Now, naively, you might have guessed that just as the electric charge comes in a nice ratio 0, 1/3, 2/3, and 1, the masses also come in a nice ratio. But it is a rather bizarre story. I show you the look at this mass ratios of elementary particles. Suppose the electron is 1 ratio. The muon is 207 times heavier than the electron. The tau is 3483 times heavier. The down quark is 9 times heavier. The up quark is 4 times heavier. Here you see a nice pattern. Squared, 1, 1, 2 square, 3 square. And this the octonions would actually come and tell us why it is like this. Look at this strange quark, 186 times the electron, 8,000 times the electron. Look at these numbers, 340,000. So much heavier. Where do these strange ratios come from? Up until now, in fact, up until 2 months back, we did not know the answer. Now, the octonions explain to us where these strange mass ratios come from. I'll show you the proof. We will be able to prove why the top quark is 340,000 times heavier than the. This will come from just from numbers. The neutrino masses are unfortunately not known. We just know that they have mass. But now see how much lighter. On the one hand, you have gone to 300,000. On the other hand, you have come down to a millionth. Theory has to explain why all this is going. So, what will be proved from the octonions? We'll prove the charge ratios. We'll also prove these mass ratios, except for neutrinos. We'll prove it for these particles for which the electric charge is not zero. This still remains to be understood. Particles interact with each other via forces. Gravitational force is felt by all particles. Something called the weak force, mediated by the neutrinos and something known as the W bosons, is also felt by all particles. So gravitation and the weak force are universal. Electromagnetic force, as you have read, is felt only by charged particles. This is what binds the electron to the atomic nucleus, the atomic force, the electromagnetic force. The strong force is felt only by the quarks. Okay? That is what binds the protons, the quarks into protons, quarks into neutrons, and binds the neutrons and protons together inside the atomic nucleus. That's a strong force. In fact, it is the strongest. Then comes electromagnetism, then the weak force, and then gravity. It is the weakest of all forces. So if the strong force is, say, 1, gravitation is 10 to the minus 40. Octonions will also tell us why there are these 4 different kind of forces. We have not yet been able to prove why gravity is so weak, but we have found out the strength of the electromagnetic force, which is what I will tell you in the third part of the talk. So, here are these 3 questions which we have come up with from our brief introduction to elementary particles. Why these ratios, particular ratios, 0, 1/3, 2/3, 1? Why such strange mass ratios, and why these 4 ratios? Now we go to the second part of the talk where I'll tell you what octonions are. So I'd like to take a pause here in case you have any questions. Are you able to follow? Is this level okay? Prithvish, or is it tough?
No, sir, it's completely fine.
Okay, so should I go on? I continue?
Yes.
Okay, I go now to the second part of my talk, the octonions. I'll explain to you what are the octonions. So we will build that story in a few steps. There are only four kinds of number systems possible in which these operations can be done: addition, subtraction, multiplication, division. Division is the toughest, the most tricky of these four operations. So please remember this. If you ask for all these operations to be possible, there are only four kinds of number systems where that can be done. Okay, what are these? Real numbers, complex numbers, quaternions, and the octonion. Mathematicians have proved that these are the only four different possibilities. Real numbers, I'm sure you have heard of. Complex numbers, also, you may have heard of. This may be new to you, so I will go through all four. Real numbers, this you know, natural numbers, 0, 1, 2, 3. Integers, when you include the negatives also, -1, -2, -3. So these are integers. Rational numbers include integers and fractions of the form p by q, where q is non-zero and p and q are integers. So like a -1, minus half, 0, 3 by 4, so on. These are rationals. Real numbers is the sum total of rationals and irrationals like square root 2 or pi, for example. So this you know, real number line, you on that you can plot natural numbers, integers, rational numbers, and real numbers. Okay, good. So this I assume you know. What are complex numbers? We ask this question: which is the number whose square is -1? You know, of course, there is no such number because the square of a real number is always positive, irrespective of whether the number is positive or negative. So, there is no number whose square is -1. So, we can say, let's go home. But mathematicians were very clever. Yes, it doesn't matter. Let us keep this number as a new kind of number, square root of -1. Let us give it a symbol I, as known as iota, or the imaginary unit, or the imaginary number. And let us pretend that we have understood what square root of -1 just by this symbol. I is that imaginary number whose square is -1. So we'll just live with it. Wherever we uh, see square root of -1, we'll keep it. If it is square root of -5, say, you pull out the 5. So it'll be 5 into square root of -1, so 5i. A complex number is a number of the form a plus ib, where a and b are both real numbers. For example, 3 plus 8i is a complex number where I is the square root of -1. Okay, I hope you get a picture now. Complex numbers are important for a great many reasons. There is a mathematics of complex numbers entirely. I make it sort of intuitive for you by saying that complex numbers can be used to explain rotation of a vector in a plane. The vector itself can be expressed as a complex number in a plane. Let's see how. So complex numbers and vectors in a plane. So here is a plane with two directions, x and y. It's a two-dimensional plane surface. Here is a vector A, whose components are A1 and A2. The X component is A1, the Y component is A2. So I can think of A vector as A1 vector plus A2 vector. But I can do now something different. I think of A1 and A2 as two components of a complex number where A1 is the real part of the complex number. The part along the x-axis is the real part. The part along the y-axis is the purely imaginary part. So I can always take a vector in two dimensions and write it as a complex number. What does it have to do with rotation? Suppose I want to rotate this vector by 30 degrees. So bring another vector without changing its magnitude. The magnitude, by the way, will be just a1 square plus a2 square. The magnitude of this vector from Pythagoras theorem is clearly a1 square plus a2 square, which is the same as the magnitude of this complex number a1 square plus a2 square. Without changing the magnitude, I want to rotate it by 30 degrees. Oh, I've written clockwise, but yeah, so okay, yeah, it doesn't matter. Actually, this is anti-clockwise going up 30, it doesn't matter. So I rotate it upwards by 30 degrees. There'll be a new vector. I want to know what are the components of that vector. Here is a very nice rule in terms of complex numbers. There are, of course, other ways to do it. Take the original vector, multiply it by the following complex number. 30 degrees is the angle you want to rotate by. Multiply it by cos 30 degree plus I sine 30 degree. That will give you this new vector B. The new vector B will have components given by cos 30 plus I sine 30 into A, cos 30 plus I sine 30 into A1 plus A2I. Now it's very simple, cos 30 is root 3 by 2, sine 30 is half. You know how to multiply complex numbers because I square will be minus 1. So you can open this and whatever values you put here will give you the final value. So what is the use of complex numbers in the present context in a geometric picture? Complex numbers help explain how to rotate a vector in two dimensions. That is this. So that brings us to the obvious next question. Suppose I want to describe rotations in three dimensions. Can I have some number which generalizes complex numbers, and yet this new kind of number will help me describe rotation in three dimensions? Clearly, the new kind of number cannot just be a complex number because this is going to give you only one angle. Whereas to describe a rotation in three dimensions, you need to be able to construct three angles. So you need something more than just one imaginary direction. And that is a problem which bothered the Irish mathematician Hamilton for a long time, for many years, in around 1840, until he finally discovered what is the new number system which describes rotations in three dimensions, and those numbers are called quaternions. What is a quaternion? Just as a complex number has two dimensions, a0 plus a1i, a complex number has four dimensions. It's a four-dimensional space made up using four real numbers. So a0, a1, a2, a3, these are all real numbers. I hat, j hat, and k hat are defined as follows. Sorry, I forgot. This should be I hat. I just wanted to distinguish it from the complex iota. This is now each of these three is an imaginary number whose square is again -1. But these are not imaginary directions of a complex number. These are imaginary directions of a quaternion, which have this. So as I said, this is same as I hat. It's a typo. I hat square equals j hat square equals k hat square equals minus one. This is the property of I, j, and k. Now it gets very interesting. I and j, it matters which order you will do the multiplications. I times j is minus of j times I. The multiplication is not commutative. In a complex number, obviously, when you multiply two real numbers, the order doesn't matter. A0 times A1 is equal to A1 times A0. Similarly, in a complex number, the order never mattered. But now the order begins to matter. I times j is minus j times I, and the I times j is k. This is the multiplication rule. J times k is I, and j times k is also minus k times j. K times I is minus I times k, and that is equal to j. This defines a quaternion, a four-dimensional number made up of four real numbers, three imaginary directions, each of which square to minus 1, and this is the multiplication rule. Without proof, I will now tell you, just like we did in complex numbers, how to describe a rotation in three dimensions using quaternions. So suppose in this three-dimensional space x, y, z, we have these three axes. Let us call this the I hat axis. So like in a complex number also one direction was imaginary in a two-dimensional plane. Now three imaginary directions: x hat, I hat, j hat, k hat. Suppose you have a vector in three-dimensional space, our real physical three-dimensional space. A vectors, for example, 2, 3, 5. In this quaternionic language, I will write P as 2i plus 3j plus 5k. In fact, this is how we can also write a vector, right? So this part of the quaternion, made up of the three imaginary directions, in fact is called a vector. A quaternion is a vector plus a scalar part. That is what a quaternion is. So suppose my original vector is this P. I want to rotate it by 30 degrees around some other vector denoted q tilde, which has components a1i, a2j, a3k. Suppose I want to rotate this vector around the z-axis. So you have to make sure that this is a unit vector divided by a1 square plus a2 square plus a3 square, which is its magnitude. So I want to rotate P around this unit vector q tilde. Okay. So q tilde for in particular could be a unit vector along the z-axis, in which case a1 would be 0, a2 would be 0, a3 will be 1 because z-axis goes with k. All right. So in order to rotate P about this or any other vector, I should know what are the directions of the other vector around which I am rotating. And I want to know how much is the angle by which I want to rotate. Suppose you want to rotate P vector by 30 degrees around z-axis, and you want to know what will be the coordinates of the new vector. Here is the answer. First, make this vector capital Q. Make this quaternion capital Q. How? Cos 30 degree, because 30 is whatever is the angle. Cos 30 plus sine 30 times Q tilde. Q tilde is here. So capital Q is now a quaternion. It is this form. This is the scalar part. Scalar part is now cos 30 degree. The vector part is now sine 30 degree into this q tilde around which you want. So Can you see what has happened in the complex number case? Let's go back. It was cos 30 plus I sine 30 acting on the original vector. Now it is cos 30 plus sine 30 into this q tilde made from all the three imaginary directions, because now there are three directions. And the new vector, this is the answer, the new vector will be q times p times q inverse. Q inverse is a reciprocal of q, because q is a number, it's a quaternion, and quaternions allow division. So q inverse is just 1 over q. 1 over q will be just 1 over this, and you know how to simplify. It's just as 1 over 1 plus I, where I is a imaginary unit. 1 over 1 plus I is 1 minus I over mod square of the denominator. So just as you know how to take the reciprocal of a complex number, you can take the reciprocal of this quaternion, multiply these three quaternions together to get the new vector to which p will be rotated if you rotate it around this direction or this axis by 30 degrees. Okay, so this is how quaternions help us geometrically, although they are a number system in their own right. Once discovered, you can study quaternions without worrying about rotations, except that I tell you something very interesting. In computer graphics, for doing rotations, this is the best method. You must find out rotations by doing quaternions. And many a time, the GPS, the satellite, which is monitoring the mobile phone signals, wants to know the orientation of your phone. So that is like 3 rotations are being made on the phone, and there is some program working inside the phone based on these quaternions, which is always doing this multiplication to find out the new direction in which your phone is pointing. Okay, so a very interesting number system. Real number, complex number, and now quaternions. In quaternion multiplication, I should tell you something very nice which you can relate to. You know vector product. In 3 dimensions, there's a dot product. Suppose you have 2 vectors, v1 and v2, 3-dimensional vectors in 3 space, v1 and v2. You certainly know what is the dot product. This is x1, x2 plus y1, y2 plus z1, z2. And you also know what is cross product. Given v1 and v2, we know there is a formula for finding the cross product v1 and v2. Now, the product of 2 quaternions subsumes both the dot product and the cross product in itself. It's beautiful. Suppose this vector v1, I write it as x1 I hat plus y1 j hat plus z1 k hat. And suppose there was some w, don't worry, let it be any number. Add a scalar w1. Here v2 is this vector written as part of a quaternion. Add another scalar w2. You know how to multiply 2 quaternions. Just open it up, multiply it out. And also you can write it as this ordered pair w1 v1 into w2 v2. By opening the quaternionic multiplication, you can show that this product is given by the following ordered pair. See, so w1 is replaced by w1 w2 minus the dot product, and this second part, the vector, is replaced by w1 v2 plus w2 v1 plus v1 cross v2. So suppose w1 and w2 are 0, you're only left with the dot product and the cross product. So the multiplication of 2 quaternions includes within itself both the dot product and the cross product. In fact, when Hamilton first discovered the quaternions, this is how Vectors were taught as quaternions. And dot product and cross product was always taught in the quaternionic language. In around 1850, the most important mathematics course in our undergraduate class was a course on quaternions. But eventually, the people who supported vectors, they won over. They thought quaternions are very weird, non-commutative multiplication. So they wanted to talk just in terms of vectors, nothing to do with quaternions. And today, most students who may not have even heard of a quaternion, but every student knows what a vector is and what vector products are. So, but they are same as quaternions. Okay, so I hope you get a picture of what a quaternion is, how it is defined, and what does it have to do with geometry and rotation. So we have real numbers, we have complex numbers, and we have quaternions. I told you there are mathematicians have proved there are only four kinds of number systems in which addition, subtraction, multiplication, and division is allowed. Three I have told you. And now the last, the greatest, and the most interesting, the most fascinating of the four, the octonion. You see how the number dimension has changed. One for reals, two for complex numbers, two-dimensional, four for quaternions, and eight for octonions. One, two, four, eight. That is it. If you go to 16, the property of division is lost. So this is the last of the four division algebras. We call these division algebras, and this is the final fourth one. It is easy to now understand what an octonion is. It is an eight-dimensional version of a complex number. An octonionic number is A0 plus A1 E1 plus A2 E2, A3 E3, A4 E4, A5 E5, A6 E6, A7 E7. The A's are eight real numbers. And as you can anticipate, each of the E's squares to -1. E1 square is -1, E2 square is -1, etc. This is what I've shown here. The product is non-commuting. E1, E2 is minus E2, E1. E3, E5 is minus E5, E3. Now for the multiplication rule, which looks complicated, but it is very interesting. Because I have to tell you, if you multiply E1 times E3, what will you get? So if you in a quaternion, I times J was K. So, but what is it? What is E1 times E2? What happens? There's a rule for that shown in this figure, which is known as the Fano plane. Very easy to remember. Draw a triangle, draw its bisectors, and draw the incircle. How many lines do we have total? 3 in the triangle, 3 bisectors, 6, and the incircle is also counted as a line. The arrows show directions, the directed lines. Okay, each line has been made into a directed line, and there are 7 of them. On each line, how many points are there? So E6, E1, E5. On this line, E5, E2, E3, and so on. On the circle, E4, E1, E2. Remember, very easy to remember, the 3 points on any given line are to be thought of as the 3 imaginary directions of a quaternion. Quaternionic triplet. E6, E1, E5 is a quaternionic triplet, and in all there are 7 quaternionic triplets in an octonion. And the multiplication rule then becomes very simple. Multiply on a line as if you are multiplying the 3 quaternionic directions following the arrow. E6 times E1 is E5. E1 times E5 is E6. and E5 times E6 is E1. Go against the arrow, just change the sign. E5 times E1 is minus E6. E1 times E6 is minus E5. E6 times E5 is minus E1. You can do for any, I'm sure you can do it for any of the other lines. Now let's do it for the circle. E4 times E1 is E2. No, E4 times E1 is E2. E1 times E2 is E4, and E2 times E4 is E1, and minus sign if you go in the opposite direction. So that is where now you can remember this for life.
So
And
why this happens?
that's the definition. That's the definition. In any number system, you have to give a multiplication rule that defines the algebra. If you want to have division allowed, it's a little intriguing proof. If you want to have division allowed, you must tell beforehand what are the multiplication rules. You understand what I'm saying? This is definition.
Yes, sir.
This is a definition. Unless I give you these multiplication rules, the number system is not defined at all. Now I have defined it for you. And as I said, this you can remember for life. You'll never forget it. Uh, just draw the 7 imaginary directions. You can choose any other number. You can set your convention. Write E4 here, E5 here, E3 here. Just label anyone in any way, make the labels 7 different labels, and draw the arrows flowing this way, this way, this way. You get my point. Draw the arrows as shown, and then you will have always remember the multiplication rule for octonions. Now for firstly, multiplication of octonions is non-commutative. That is obvious here. Ey, is minus Ej, Es. As a result, that means if you take two octonions O1, O2, it will be not equal to O2, O1. There is something more tricky which octonions don't have. Now the multiplication also becomes non-associative. O1 times O2, O3 is not equal to, oh, I made a mistake. I mean O1, O2 here. Order is kept same. Sorry, this is not O2, O1. This is O1, O2. You multiply O1 and O2 first and then multiply it with O3. That is different from doing it this way. You know, associativity is that it doesn't matter which pair you multiply first. Quaternionic multiplication is non-commutative but associative. Octonionic multiplication is non-commutative and non-associative. Okay, so now I have told you about the numbers in 4 division algebras, and I am now at the last part of my talk, almost done, unless you have any questions.
Okay, so actually there is one question
Hmm?
from a participant. So it's, sir, can you please recommend me any good math book to understand the math used in this lecture?
For the octonions part?
Yeah, I think so.
Yeah. So there is a author called John Baez, Baez. Under his name, just look up Google octonions. You'll find a very nice review article by him. And there is a book by Dre and Minogue on octonions. So you can email me. You just email me, get my email address from my website. I'll send you the references on division algebras, quaternions, and octonions. There are some very nice books. Any other question? Okay, let me go to the third and the most interesting part of my talk. I have told you two different things One was elementary particles, and I left with a few open questions. And then I introduced to you what are octonions. Now I want to tell you what do the octonions have to do with elementary particles. Numbers describe physical space. There is a very natural way of going from numbers to geometry. For example, this you are used to. Real numbers are numbers, but you represent them on a real line. The line is a part of geometry. Numbers are part of numbers. So every number system, the four number systems that we have introduced, each of them can be related to a physical space. So real line is a one-dimensional space. Our universe is three-dimensional, three spatial dimensions represented by three real numbers. One real number along this real line, another real number along this real line, and a third real number along. So three real numbers, obviously 2, 3, 5. These are three different real numbers for three directions. In physics, particles move in space. So you might think of a one-dimensional space in which particles move. Suppose an ant is moving along this line. So physical particles, like including elementary particles, they move around in space, and their dynamics, their laws of motion is what most of physics is about. This is a three-dimensional space in which you might, when Newton's apple falls, it is a particle or an object executing motion in space, and you have mapped space to real numbers, or you can map real numbers to algebra, can be mapped to geometry. Geometry can be mapped to algebra. For real numbers, we are used to it. We can do it now for our other division algebras. We can do it for complex numbers. That is very straightforward, though. Let me straight go to quaternions. What is the kind of physical space that is associated with quaternions? If you have some familiarity with Einstein's theory of special relativity, you will know that the space and time together define a four-dimensional space-time. Three directions of space, one direction of time, but time is different from space. If space has three real directions, the time direction is imaginary. Or you could do it relatively. Space has three imaginary directions and time has one real direction. What does that remind you of? One real direction, three imaginary directions. Lo and behold, that is a quaternion. Space-time is correctly described in Einstein's theory of special relativity by nothing but a quaternion. So here is the time axis, and I have shown you only one space axis because I don't know how to draw four dimensions and visualize it. So this is the path of a particle. We call it a world line. So at this time, the particle is here. Take any point on this line, it will tell you that at this time, the particle is here. So the space-time, our space-time, as Einstein explained to us, is described using quaternions. However, there is no restriction on the properties of particles such as charge and mass. Take care. I put a charge particle here. It can have any electric charge. It can have any mass. So I'm preparing you for what will come next. In our ordinary three-dimensional space, if a particle moves, the space is not putting any constraint that you must have this much charge or that much charge. Neither are the quaternions putting any restriction, but this changes completely when we go to the octonion. So this is the reason why octonions and elementary particles are related to each other. Today in physics, including my work, there are reasons to believe that space-time has 8 dimensions, octonionic dimension, not 4. The other 4 are very thin. So this defines the space. If it was only three-dimensional space, it would be E1, E2, E3. If it is four-dimensional space-time, it is a quaternion A0 plus A1 E1 plus A2 E2 plus A3 3. But I'm saying to you, it seems that our space-time in which we live is not four-dimensional but eight. It has 7 spatial directions, one time direction, together 8. So, as if the space that we live in is described by octonions. In such a space, it has been proved if you put a charged particle, the ratios of the electric charges of all charged particles can only have the values 0, 1/3, 2/3, 1. If you knew nothing about electrons and down quarks and neutrinos, suppose you knew nothing, but you were studying electricity and magnetism in an octonionic space, you could have proved that there are only 4 kinds of charges in elementary particles, and you would have said these are called neutrino, down quark, up quark, and the electron or their antipart. So I hope you get some sense. I have not given you a proof, but the non-commutative, non-associative nature of this spacetime is such that it puts a geometric. It's like, give you an example like violin. What is a violin? You have a stretched string tied at both ends, and if you play the violin, only certain frequencies are allowed. If the wire was not tied at the two ends, you could have all possible kinds of frequencies. But because there is a boundary condition, there are special conditions, only certain frequencies are produced. In the same way, it can be proved that there are properties of this space-time which restrict the allowed values of the electric charge ratios. Not just that, the actual value of the electric charge is also determined when you place electromagnetic particles, electrically charged particles in octonionic spaces and study their elementary particle physics. You can prove this famous result known as the fine structure constant. It is known from experiment that it takes this famous value 1 by 137, but nobody knew why this number. And we have shown using studying particle physics on the space-time of an octonion that the electric charge of the electron, square it, divided by these constants, Planck's constant and speed of light, you actually get to prove this from first principle. So if you did not know any experimental particle physics, you could have proved that charge takes only these values and the electric charge of the electron satisfies this condition. This constant is known as the fine structure constant, and now we have derived it for the first time from the study of particles on octonion space. The same amazing thing comes out to be true for masses, mass ratios. Remember, I showed you those crazy numbers, 2,480, 3,000, 340,000. Those strange looking numbers are actually these simple fractions. This I proved 2 months back in my work on octonions. And these are square root mass ratios, not the ratios of the masses, but of the square root of the masses. If the down quark is 1, We showed that the up quark is 2 by 3, the positron is 3, 1 by 3. Remember, you saw 1, 4, 9. So if this is 1, this is this will be, this is 1, so 3 times, no? This is 1, this is 9, and this is 4 because it is square. These are square root masses. And these fractions are much simpler than those numbers like 340,000, 2,487. What is there in these fractions? Only thing that is used is 1, 1/3, 1, 1/3, 2/3, and this square root of 3 by 8. By the way, this is not cooked up. This is not just numerology. This follows from studying the algebra of the octonions that only these mass ratios are allowed. Now let us compare with experiment. Let's convert this into decimals, okay? You can just take a calculator. You have a recording of this talk. Go back home, convert all this into decimals. Those are the decimals that I have written here. Right hand side is the experimental number that has a error bar range, minimum and upper value. Left hand side are these fractions that I have derived and predicted. You can compare for your, the match is not exact. We are still trying to understand why there is a little departure. But you see overall 14, 14 mu1 to electron square root mass ratio, tau lepton 2 electron 58, 58, 58. Charm to up 23 lies in the range 21 to 26. 289. This is the 340,000. If you take the square root of that, it will give you this. And this lies within this error bar range very comfortably. So the top quark to up quark mass ratio is derived. 4.16 is just outside this range. 28 bottom to down ratio is within this range. So we have been able to prove why those strain mass ratios, because the octonions control mass ratios. You cannot put arbitrary charges on octonionic spacetime. Neither can you put arbitrary masses. The spacetime determines what is allowed, and this is what we did not know so far. So if we accept that our spacetime is 8-dimensional and described by the octonions, we get the answer to our questions, including the answer to the question for why there are 4 different kind of forces. The octonions dictate that only 4 kinds of forces are possible. So the fact that charges have only the ratio 0, 1/3, 2/3, 1 was proved in this beautiful paper by this physicist by the name Cole-Fury in 2015. And just this year, I inspired and by building on the work of Cole-Fury. She showed why charge has those values. I showed why masses have these ratios. This is still under review, but this paper is published. The derivation of the fine structure constant 1 by 137. So this is what was done in that paper. In this paper, I derived mass ratios. And sorry, one moment, we're almost done. The octonion spacetime, if you do physics or particle physics on that spacetime and study the forces, basic forces of nature and their unification, the octonions actually show that there are only 4 known forces, and those are the same ones that I talked of: gravitation, weak, electromagnetic, and strong. We proved that those are the only 4 forces allowed if your space is octonionic. Hence, and these are unified into one force. It's like Einstein's dream of unification. So we now have a candidate theory of unification of forces. More work needs to be done. We have to predict more. That's why I call it a candidate theory, not the final confirmed theory. However, you have all heard of string theory. This new octonionic theory, it is much more successful than string theory. String theory tried very hard. It was even called the theory of everything, but I think unfortunately we have to now call it the failed theory of everything. It was a great attempt, it did not work because string theory cannot tell us why charges come in those ratios 0, 1/3, 2/3, 1. There is no proof. Neither can it tell us that why the masses have those strange ratios. So string theorists actually came to a very strange conclusion. All charge ratios are possible. All mass ratios are possible. In different multiverses, different ratios occur. In our, we happen to find, we are living in a universe where the ratios are 0, 1/3, 2/3, 1. In some other universe which we have not even detected, the ratio will be something else. That is not called physics, that is called failure. We would like to believe that there is a fundamental theory which predicts and explains why our universe is what we see it to be. And the octonionic theory is one such example where we have actually been able to prove why the universe the way it starts from mathematics. You see, pure mathematics and number theory with no free parameters, just relating the physics of particles to the space-time of octonions. This is my last slide. Octonions were discovered by John Graves, an Irish mathematician, in 1843, and now more than 150 years have passed by, and we finally now realize that octonions are very important to physics and particle physics and also to gravity. So all the four numbers, the real numbers are important, complex numbers are important, quaternions are important, and the last of the four division algebras is the most important. There is no more division algebra. This is the last, and fortunately, we are able to explain what we see in the universe using this last of the four division algebras. So my thank you to Professor Graves for inventing, discovering octonions, and my thank you to you very much for patiently listening to me. And this is the end of the talk. I can stop sharing and maybe we can have the gallery view.